to Andy Brown, our Director of Research. I just want to give you a few housekeeping points. This webinar will be recorded and it will be made available on the implementation Confluence page and on this event registration page. We will also make slides available, and you can ask questions in the Q&A section, but you can't open chat or camera, so please put your questions in Q&A and we will answer them either there or later after the presentation. And with this, I give the floor to Andy.
Okay, thank you very much, Milana, and good morning, everyone. As Milana says, I'm Andy Brown, Director of Research at ECMWF, and it's my pleasure to introduce the Cycle 49R1 that we'll implement this autumn. We have an annual rhythm of cycles, so about a year or so ago, I was telling you about the major innovations in 48R1, in particular the 9-kilometer ensemble, and I hope today I can do justice to what I think is another very strong cycle. So I have a rather scary side with a long list of contributions. You'll be pleased to know I'm not going to read all of this out, and I don't expect you to read it all. And as Milana said, we'll make the slides available. But I think the immediate message is, as ever, that the cycle is made up of a lot of different contributions, and there's a very meticulous process of bringing these all together. Now I'll have slides on sort of many of the key innovations in what follows. But I just wanted to very briefly sort of touch on a couple of the things that won't come up again, which are also important in their own right. So there's an observations package, which includes assimilation of ground-based GNSS data, and also use of the shortwave infrared channels on the CRIS satellite. Moving down to the VAR-QC and stratospheric balance. So VAR-QC, that's our variational quality control, how we sort of check for the quality of observations. And at the moment, we don't do that check in the first minimization of the data assimilation. And there have been one or two examples with tropical cyclones where a very spurious observation has caused trouble. So we're changing there to be just one step more conservative in our use of observations. And on the stratospheric balance, so we're reintroducing stratospheric balance in the 4D VAR, and also increasing the use of GNSS RO data, so using it up to 60 kilometers rather than 50 kilometers, and also giving it more weight. Numerous physics and numerics contributions, which I can't possibly do justice to. I'll maybe just mention an improved 10-meter wind diagnostic that's a contribution to the scores that I'll show later. Maybe just at the bottom there, other technical neutral changes, but one very significant change there is, as you know, a year ago, we moved to our ensemble system being at 9-kilometer resolution, exactly the same as the high res. But for purely technical reasons, the ensemble control and the high res forecasts weren't bit identical to each other. There was no sort of science preference of one over the other. It's just for historical reasons, things were done slightly differently. And we've now eliminated those differences. So ensemble control and high res, in terms of the forecasts they produce, are absolutely the same as each other from 49R1. And that's part of our strategy to really moving to we will just have an ensemble system, so an ensemble control and perturbed members. So just to run through some of the sort of the key highlights of this cycle. So first of all, on the use of observations, so major developments on the microwave assimilation, and also the use of the new version of RT-TOV, the fast radiative transfer. So on the use of observations, I think probably the most significant thing here is increasing the density of observations we're using. We've been gradually increasing the resolution of our data assimilation inner loops, and so in parallel with that, to get the full advantage of it, we also want to increase the resolution we're using the data at. So this is for the microwave humidity sounders. If you look on the right at 48R1, so the current operations, we thin this data to 110 kilometer spacing. And at 49R1, we'll both super-ob the data and we'll use it at 70 kilometer spacing, so less thinning. And that actually increases the amount of 183 gigahertz data we're using by a factor of 2.4, 140% increase in the amount of data. So getting more value out of the satellite data. A second strand is we set out a few years ago on what we called the all-surface strategy. We've worked for years to use microwave radiances, not just in clear sky conditions, but also in cloudy conditions. But we still don't make full use of it over a lot of difficult surfaces. We haven't had the science to be able to decouple the surface effects from the atmospheric effects. So this is one really important step in that spirit. So first step is developing a new hybrid empirical physical model for the emissivity of sea ice. So that was trained in a machine learning context. So a hybrid physical machine learned prediction of emissivity. And if we use that, we can start using the GMI and the AMSA2 imaging channels over sea ice for the first time. If you look at the panel on the left, there's Antarctica in the middle, and the sort of the dark colors show the amount of this data that we're using. And you can see the ring, the white circle around Antarctica, where we're currently not using any of this data. And if you look in the right-hand panel, that's what we'll be using at 49R1. So, you know, by having this better emissivity, we can start using this data in places we're not currently using it. And if you look at what that does to the forecast scores, you can see, so this is temperature, root mean square error, cross sections, latitude on the x-axis, pressure on the y-axis in different time range, and blue colors are good and red colors are bad. And you can see it, yeah, in the southern hemisphere, in these regions where we're using this data, it improves the forecast out to day 3 or so. Aspect of the assimilation developments is we've previously not assimilated synop temperature. We've used humidities by day, but not used temperature from synops or humidities by night. And so this is a change to actually assimilate the synops temperature and humidity day and night. And this has a very strong positive impact on 2-meter temperature. So the right-hand plot is change in root mean square error of temperature for the northern hemisphere winter. And you can see we're getting 5% or more improvement at short range, but still out a few days in, seeing noticeable benefits in the quality of 2-meter temperature forecasts. There's more details in the newsletter, but this is one part of a particular focus of this cycle has been to improve 2-meter temperature forecasts. And this is one contributor to that, but I will show others as well. So in that vein, here's another 2 developments which also improve the 2-meter temperature forecast. So this is now in the land data assimilation system rather than the atmospheric system. But that has to take 2-meter temperature as an input to the land data assimilation system. And this is introducing a correction for where the 2-meter height in the model and in the real orography are inconsistent with each other, how we deal with correcting that temperature. So introducing a lapse rate correction in the land DA system. And if you look at the panels, again, blue colors are good. This is change in root mean square error of 2-meter temperature, and you have blues and greens. So that improves 2-meter temperature. And on the soil moisture analysis side, we have a background error that we specified for the soil moisture analysis. And here we're increasing the background error in the soil moisture analysis. And similarly, you get the blue colors through the atmosphere. So we're improving temperature, and in particular 2-meter temperature, through that change to the background errors in the land assimilation. The last change in this spirit is changing some aspects of the snow data assimilation. So how we thin the IMS product snow cover before assimilating it. And also we haven't previously been able to assimilate the IMS snow cover in very mountainous areas. So we've been using the IMS snow, but not in particularly in mountainous areas. But in combination with developing new updated snow cover diagnostic, we've now got to a position where we can assimilate this data with benefit. So the figure on the right is another of our sort of typical scorecards. You know, the northern hemisphere in the first 2 columns, and then southern hemisphere and tropics, various different measures down the y-axis, and the blue colors showing that better using and more using this snow data is improving forecast actually very widely across the Northern Hemisphere. And again, the panel on the left showing a further contribution to improving temperatures. The last aspect I wanted to touch on the data assimilation is we don't just run one data assimilation, we run an ensemble of data assimilations. There's two main purposes for that. One is to get errors of the day, so the background error that the 4D VAR uses is taking advantage of information from the EDA, and it's also used as part of the ensemble initialization. But although our main ensemble forecasting system has been at 9 kilometers since 48R1, the ensemble of data assimilations was still at 18 kilometers. And in this step, we're moving it from 18 kilometers to 9 kilometers, and its inner loop changes from about 100 kilometer resolution to 50 kilometers. So a much higher resolution ensemble of data assimilations. And I'm not going to go into the details, but there's some very, very clever work behind the scenes on soft-centering. So to make this affordable, rather than making all members the same, effectively, there's one particularly accurate control member of the ensemble of data assimilations, and the perturbed members take advantage of information from that. This is really quite a significant change. So the plots here, temperature as an example, but just looking at the impacts of the new EDA on the spread, or on the EDA's spread. And so the red colors mean we have more spread with the new ensemble of data assimilations. And if there were any blue colors, it would mean less. But the left panel is just showing the effect of that higher resolution EDA. And you can see significantly more spread. The second panel, I'll come to the change to the stochastic physics, but this is the change to the stochastic physics, the SPP scheme, which we also implement at the same time. And that also gives an increase in spread, very particularly in the boundary layer. So we have a general increase in spread, but also a complicated geographical and height variation in that spread. So that affects the background errors. And if we look just as a measure of, is that working? When we use these new background errors in the 4D VAR, we would hope we would fit observational data better. So this is the standard observations minus background plots that we look at. 100% is where we currently are. And if we're moving to smaller background standard deviations, so to the left of that vertical line, then we're getting a better fit with these new background errors. And so the top left, you see the humidity channels from IASI. Then in the middle, you have AMDAR, humidity measurements, ATMS, the humidity channels on the top, and so on. So we can see that we are fitting the data better with this new EDA. Now we'll move to some of the model contributions. So first of all, various updates to convection. So, for example, changes to the assumptions about the liquid phase in mid-level convection, and that helps with the shortwave biases and cold air outbreaks and storm tracks. And also some changes that improve the nighttime convective organization. There's also some changes on the product side. We've been sort of tidying up and improving the various convective diagnostics on CAPE and SYN, and also over the years, continuing to develop the clear air turbulence parameterization. So just to give a forward-looking advert, there'll be a further webinar on the 11th of June where Mathieu, our head of evaluation, will talk more specifically at the sort of the products and most immediately sort of user changes, the changes that the users will see. Also made major developments to the wave model. First of all, it goes to a higher resolution, so now running on the same grid as the atmosphere. To save a bit of cost, we do reduce the number of frequencies we output in the wave spectra. But maybe the most significant scientific change are changes to the wind input parameterization. So that effectively changes how the drag coefficient varies as a function of wind speed, and also will then in turn change the heat and moisture fluxes. And that has a strong impact over the oceans. The scatter plot on the right shows the winds in 48R1 compared to the winds in 49R1. If I sort of really want to draw your attention to the circle, the changes to the drag coefficient mean at sort of, in mid latitude storms, wind speeds 25, 30 meters a second, 49R1 with this new wave model parameterization tends to have higher winds than we've had previously. And that's good, but that addresses a known underestimation of extreme ocean winds. The big package of land surface contributions. First of all, we implemented an urban tile for the first time, so a simple sort of urban energy balance. So as well as having forests and grass and lakes and whatever else tiles, we now have an urban tile, which we know represents urban heat islands. We've updated the vegetation and leaf area index maps so that the data sets we were using were quite old, so we've taken new information from the ESA Climate Change Initiative and updated. The typical effect is we end up with relatively more low vegetation than we had before and less high vegetation. There's also improved seasonality in the leaf area index. Also, other changes, including details of the 2-meter temperature diagnostic and the soil moisture stress function. I already mentioned the stochastic physics. So for many years, we've used the SPPT scheme and it served us very well. So that effectively, it's representing the model uncertainty. And what that does is effectively scales the physical tendencies up and down in a random manner to represent the uncertainty. For many years, we've been working to replace that with SPP, which was where we perturb uncertain values in the parameterization rather than the outputs of the parameterization. And sort of schematically at the bottom, we show sort of the difference between those two philosophically. So the current scheme, SPPT, takes the physical tendency output and scales the whole thing up and down. SPP, on the other hand, can, for example, make convection go to a different height if you put in different entrainment rates. And we also perturb the surface fluxes and get more spread in the boundary layer. So the impacts of this, it gives us local conservation of moisture and energy that we didn't have before. We get a lot more spread in the boundary layer, I think, as I previously showed. The existing SPPT scheme, we have to, in a way we wouldn't really want to, taper down the contributions near the surface for stability. We have, with this scheme, beneficially much more input near the surface, and that improves the 2-meter temperature and particularly the 10-meter wind, and has some beneficial effects on the extended range and seasonal frequencies. And I'll show some results on tropical cyclones because it does tend to increase the frequency of tropical cyclones, which I'll come back to. Last one, another busy slide, but again, the slides will be available. So as well as the NWP and extended range systems, we'll be updating the composition, the CAMS composition system. There's a lot of developments here. I'm just going to highlight two key ones. The first one is new anthropogenic emissions. Of course, air quality and composition predictions, very sensitive to the emissions. And there's been a lot of work done to move to more up-to-date versions of the EDGAR emission data set, taking into account more recent socioeconomic data, so more accurate emissions, and we can see that improves the forecasts. And also major developments to the aerosol model, particularly the removal of aerosol, whether it's the deposition and secondary aerosol formation. So I hope that's given you a flavour of the very many contributions that are going into this cycle. So what does it all add up to? How good is it? I think I said we really set out on this cycle, hoping to improve as many things as possible, but with 2-meter temperature as a real focus. And so here's some scores for the Northern Hemisphere winter. So we have time range on the x-axis. The left-hand panels are the root mean square error of the ensemble mean. The right pairs of panels are the ensemble score, the CRPS score. And the top panels are the difference, but the bottom panels are just more directly showing the 49R1 results in red and the 48R1 results in blue. And I think you can just by eye, you can see there's clear blue water between those. It really has made quite a dent in the 2 meter temperature forecasts. There's some sort of numbers quoted on the right there, but sort of, typically sort of, 4 or 5% out to day 5 for the Northern Hemisphere in the winter. If we look at 10 meter wind, maybe even more striking, the differences here. And while the 2 meter temperature forecast improvements are largely Northern Hemisphere and largely winter season, the wind verification scores tend to be significantly improved all through the year. And you can see that the sorts of numbers we're talking around, depending exactly what range you look at, but 5% is not uncommon for improvement in these 10 meter wind scores. I look at the whole scorecard. So the details of this don't matter, but this is our usual scorecard. So the top half in each case is verifying against own analysis. The bottom half is verifying against observations. And then you have pairs of columns for the Northern Hemisphere, the Southern Hemisphere, the tropics, and Europe. And on the left, we have the ensemble control. As I said, that would be the same as high res, but I'm deliberately using the new nomenclature. And on the right, we have the perturbed 50-member ensemble forecasts. So blue is good, red is bad. And I think you'd agree it's pretty overwhelmingly blue. If we want to quibble, maybe the few exceptions are up at 50 hectopascals in the stratosphere. There's some degradations. Mean wave period against analysis looks slightly red, although it's difficult to verify observationally, although we have some reason to think that the swell dissipation we might look at further. Maybe the last thing I'd raise is there are some sort of mild degradations in a few of the sort of the tropical scores. Effectively, that's, as I said, the EDA and the stochastic physics changes make very big changes to the spread and not uniform changes, geographically and height dependent. And so in the end, we have to do a bit of a compromise in how we're weighting the background errors compared to the observational errors. And we could optimize away some of those tropical reds, but at the expense of other things that we think are more important. But overall, I hope and think you'd agree, this is a pretty compellingly blue scorecard. And as I've shown, particularly the near surface verification is very strong. Just a few slides on tropical cyclones. So if you look at the ensemble control, I don't think there's much to say. The changes in position error or intensity error, I think you would struggle to say it was statistically significant in any direction. If you look at the ensemble scores, again, it's always hard to pick out a clean message, even with a strong sample. But if maybe just look at the top right panel, the blue is 48R1, and the red is the new 49R1. The dashed lines are the spread. So what we are seeing is we have considerably more spread in the intensity of tropical cyclones. So across the ensemble member, there's more spread. Now at shortish range, that's a good thing. You can argue whether that's a good thing at longer range. A couple of other tropical cyclone aspects I did want to draw attention to, though, is if we look in the ensemble initial conditions, so this is the T+0 forecasts. So this is just arbitrarily chosen tropical cyclone Freddy and just showing the first 10 members. But they're completely illustrative of what it would be if I tried to squeeze 50 members on the panel. And I think, if you look at these, some of them don't look very realistic. They're slightly a bit non-axisymmetric at T+0. I mean, the good news is I think that's largely a cosmetic thing, because if you look in the model forecast by 12 hours out, this has resolved itself. But actually, this is an almost inevitable artifact of how we create the ensemble initial conditions by recentering the ensemble of data assimilations on the main 4D VAR analysis. And because the ensemble of data assimilations is higher resolution, it creates deeper structures itself. And so if it's trying to make a tropical cyclone that's not quite where the recentering analysis wants it, it can make some slightly strange structures. As I say, I think it's mainly a cosmetic issue, but we have got, you know, work in hand, and I think that that will be addressed at the next cycle. The last tropical cyclone plot I wanted to show was, this is just looking at the sort of the numbers of tropical cyclones in the ensemble system. So we have wind speed on the x-axis and the number of tropical cyclone instances between 5 days and 10-day forecasts on the y-axis. And the thick red line is where we currently are operationally with the 48R1 perturbed forecasts. And the thick blue line is where we are with 49R1 perturbed forecasts. And the black line is the IB tracks of observational data. And so I think what you can see is that with SPP, we do systematically have more tropical cyclones in the ensemble members than we do with the current operational system. Now, you can argue that for the very weak tropical cyclones, that may be a bad thing. It may be overdoing it. For the stronger, more significant tropical cyclones, we were significantly under before, and that's a move in a good direction. So we need to look further, but I think overall, that's still a move in a good direction for the deeper, more impactful tropical cyclones. In the last couple of results slides I have are extended range and seasonal. So when we upgrade the medium range forecasts, we automatically upgrade the extended range, the monthly forecasts at the same time. This is a very busy slide for the impact of the new cycle on the extended range forecasts. But I think the absolute headline of the headlines is it doesn't do very much. If you look on the left panel, the weekly mean anomaly skill scores, or the bottom right panel, Euro-Atlantic regimes, it's really pretty neutral. So it's not doing anything very good. It's not doing anything very bad. If you look at the MGO, I won't go through the details of the plots, but some improvement. Week 3 and 4, correlations for the bivariate index are improved a bit, and the spread error is a bit better in this. So some improvements in the MJO, but over the piece, not very dramatic in any direction. And this is really an aside that I'm not talking about this in this webinar, but again, a further plug for the forthcoming user meteorological webinar. There is a change in the reforecast configurations for both the medium and extended range at 49R1. So if you're a user of ECMWF reforecasts, it's going to be different at 49R1, the scheduling of how the reforecasts are done. So please, if you're a user, do follow those changes. On the seasonal, so we don't upgrade the seasonal system with every cycle. So the last time we had a new seasonal system, SEAS5, was in 2017. But we routinely check, because we're always expecting at a future cycle to do a new seasonal system. And indeed, the next system, SEAS6, will be operational in 2025. So we always want to look that the science directions we're taking are going to support a better seasonal system in the future. So we've had a look at what 49R1 does on seasonal timescales. I think the most significant thing, again, is the change of the stochastic physics scheme, which changes the spread error. It tends to reduce spread at seasonal timescales. And on the whole, that's a good thing. It's bringing our sort of spread error ratios back closer to 1. If there's a caveat to that story, it's that over a few years, our cycle spread error ratios seem to have grown away from the current operational seasonal system. So the spread error, not quite as good as they have been, but this 49R1 upgrade gets us back to more or less where we were. So I think my final slide, just to sort of give you an idea of the timeline. So we announced the cycle earlier this month, obviously the science webinar today. We'll talk more about this at our user meeting on the 5th and 6th of June. And then, as I've mentioned a couple of times, Mathieu Chevalier will be giving a further sort of meteorological technical webinar on the 11th of June. Then we'll start the release candidate phase in June. We normally run those for about 3 months, but because it's going to be over the holiday period, so there'll be about 4 lapse months of that. We don't have an absolutely definite date for implementation, but October, maybe November 24. Certainly this autumn is the target for implementing this. And I say, I hope I've convinced you that there's developments in it that are going to make it a better cycle. So with that, I think I will finish.
Thank you very much. And it might happen that people can't post in Q&A. So we have a raised hand, and I will, if the person who raised hand can raise it again, so I can unmute them. Then we can. If the Q&A doesn't work for you, please raise a hand and I will unmute you.
Ilana, just before we have any other questions, there was one question in the chat, which was, do we know if the changes to the land DA improved the soil moisture relative to observations? So my response in the chat is, I don't know the answer, and it's probably something we'll have to take to the land DA team to deal with. But if anyone here does have an answer, then please share it now. Otherwise, we'll take this one offline.
Yeah, I would feel more confident getting the direct answer. There is, ideally, the land DA changes simultaneously have a positive benefit on the atmosphere and improve the direct sort of soil moisture as well. I think historically that's not always the case, but yeah, I would suggest the land data assimilation either now or after the event give a more definitive answer rather than me giving something inaccurate. Are there any further questions? I can't see the chat, so I'm reliant on my colleagues to relay anything.
Yes, there is. No problem. Question. Any info on ensemble higher resolution extension to 15 days? Will it run before the main ensemble?
Well, I mean, the general comment was that sort of most of the detailed questions on sort of scheduling and things. I would recommend anybody with interest that follows Mathieu's webinar. But I think the ensemble control will run on essentially the schedule of the current high res. So yeah, so the ensemble control will be available before the rest of the ensemble. So as now, effectively.
I will wait a little bit, but that's all the questions. Oh, there is one hand, sorry. Okay, I have allowed. Oh.
Okay, my name is Lea Saukonen and I'm from FMI, Finnish Mets Institute. My question is just the way the operational weather forecasters are working with these models, and I wonder, when we get the new one, have you any idea, will it take longer time to run it? So will it come a little bit later, or is it exactly the same time, or even earlier? Thank you.
I don't think it will change much. I mean, I can't promise a plus or minus a minute, but I don't, and unless any of my colleagues want to contradict me, I don't think we think the cost is very different of this. And so I think my starting point would be on the same sort of schedule as now. And now, as previously asked, with this sort of the ensemble control that replaces the high res ahead of the main ensemble. But there is the new system of data being provided as soon as it's available, rather than always waiting for the same time before we start disseminating.
Thank you.
Okay, thank you. And now we have a few questions. There is one question about the ERA 6. Is the ERA 6 data available for download? But that's off topic a bit.
It's off topic, but also the ERA 6 hasn't been produced yet. We're working to finalize the configuration now, so ERA 6 production will start in the early part of next year. So it'll be a couple of years down the line that ERA 6 will be available. But I think it does promise to be a very exciting reanalysis. So it'll be a 13, 14 kilometer resolution rather than the current resolution in 30 or so kilometers. And there's a lot of science innovations in it.
We have two more questions for now. 48R1 had degradations in the T50. I guess this is temperature in 50 hectopascal. That was said we're going to be addressed in this cycle, and it seems like T50 has degraded again. Is the work being done to correct this?
Yeah, I guess we are always sort of constantly trying to sort of juggle, trying to improve all the different aspects of the forecast. So yes, we need to keep working on the T50. I would love everything in the scorecards to be blue. Yeah, I guess it's back up. That is one exception for this one. Although I think it's against analysis you see it most strongly.
Will the high-res time resolution stay 1 hour, or will it change to 15 minutes?
I'm not aware of a plan for change, but then again, that feels very much one for the sort of meteorological webinar or my sort of forecast department production colleagues to sort of provide more information if there is any significant change.
Yes, so this one is more for the 11th of June. And now there is a really long one. My question is about, is it planned to implement the non-hydrostatic formulation in the physics of the IFS model in the near future? I don't know if it is appropriated in global models regardless of mesoscale resolution, although I know that the major influence of the issue is the precipitation forecast. From our experience in Canary Islands, the improvement of the 10-meter wind forecast in complex orography, where it is currently very poor quality.
Okay, so the short answer is there is no plan to go to non-hydrostatic for the operational ensemble at 9 kilometer resolution. As part of the Destination Earth work, where we're running 4 kilometer simulations experimentally, we have been looking at 4 kilometer resolution at comparisons between non-hydrostatic and hydrostatic to see has that crossed the point where the cost benefit changes. Now, if you look hard enough at 4 kilometers, particularly say over the Himalayas, where gravity waves are non-hydrostatic in reality, we can see that the non-hydrostatic model performs a bit better over the Himalayas at 4 kilometers. But I'd say in a global sense, even at 4 kilometers, the evidence for major improvements, certainly in a global flow sense, is not very compelling. But so to go back to the original answer, in terms of sort of operational forecasts at 9 kilometers, no, I don't think there is a case for the extra cost of the non-hydrostatic. But we keep under review for when we go to higher resolutions, when there's clearly a crossover somewhere.
Thank you. So there is a question and a comment. Really interesting update. The changes look useful in terms of model performance. I'm guessing that later AI could be added.
Yes, I mean, we're very, very active on machine learning. So well, I guess there's different aspects to this. There's machine learning within the forecast, so sort of doing hybrids of physical approaches and machine learning approaches. The example I showed with the emissivity modeling to let us use the satellite data better is already an example of that. And we have, ambitious plans in research for further doing work to get to hybrids of physics-based and data-driven methods. And then separately, you may have seen our various communications on our efforts with the sort of the fully data-driven methods that the AIFS. So yeah, absolutely, yes, very high up the agenda.
Thank you. Great update. I'd like to ask you about improvements of general. You mentioned that there are several contributors for this improvement. Is it possible to detect which contributor has the greatest impact, or any studies in regard to this?
Well, yes, I mean, I think essentially we know, because the way we create these cycles, that big long list I had where it was V1 to V11, effectively we do initial trialing of all of those things on their own, and then we start bringing them together and trialing things together. So I mean, I think I tried to bring out some of the bigger impacts as I went through. Now, certainly in terms of 2 meter temperature, the synop assimilation, the land data assimilation changes, the snow changes, and the new land maps are all very relevant in that context. For the wind improvements, the stochastic physics upgrade is in giving us more spread in the boundary layer is very important for those. So yeah, I couldn't off the top of my head quantify it. It depends what variable you're looking at, but yeah, hopefully presentation today can give you some sense of the sort of where different contributions are contributing.
Thank you. Will there still be HRES run and control run in the future if there is no difference anymore?
Again, probably you'll get the more authoritative answer in the next webinar, but I think just for user convenience, I think that they will literally still run at 49 R1, but the plan is at 50 R1 the forthcoming cycle they won't. So because yeah, there is no logic anymore now that they're the same. So we're definitely on a route to just having an ensemble control and the ensemble.
Thank you. Do you have a map showing the improvements in wind speed at 10 meter in 49 R1?
Not to hand, but I'm sure we have it.
That is all that I can see at the moment. I will give it a minute. Sometimes they can show later, but nope. So with that, we can end the webinar. The recording will be available on the implementation Confluence page and on the event of this webinar page. Thank you all for joining, and thank you, Andy, for presenting. And of course, you're all welcome to join us in the webinar on 11th of June at the same time, where our head of evaluation will present more user-oriented updates in the next cycle, as well as some more evaluation. Thank you.
Okay. Thank you very much, all.